All right, it's 1 o'clock, so let's go ahead and get started today. All right, so good afternoon, everybody. How's everyone doing on this fine Tuesday afternoon? Weather's finally cooling down, so that's a good thing. It was last month has been kind of weird for me because I was kind of in and out of sickness for the whole month, so felt like sometimes I couldn't tell if I was having a fever or it was just really freaking hot outside because the airflow in my apartment's not super great. So when it gets hot, it really gets hot here. So I'm glad that it's cooling down. But apparently it's going to go up again this weekend, so not looking forward to that, that's for sure. Okay, so we're in week 2, so this is our first lecture in week 2. And so before we begin today, I want to thank everyone who filled out the minute papers last week. So remember those minute papers, I read all of those and I use the information from those minute papers to help improve the class. Especially for this, format, which is, it's kind of a new thing for all of us. So, just because this is virtual, I want to make sure that, this class is going to be the best that it can be. So I think generally the feedback that I got was last week there was a lot of definitions. So I hear you. There were a lot of terms, and I think a lot of terms that you might not be familiar with. And unfortunately, that's kind of just how this is. So the way this class is basically, we're learning economics as engineers, so we kind of have to build up everything from scratch. And usually the first thing that we do is we learn all the definitions. So I know it's a lot, and I know it's a little bit overwhelming at first, but just kind of stick with it. There's going to be a lot of new terms today too, but over the next couple of weeks, you'll see that you're going to use all these terms and you'll kind of see them in action, and they'll start to make more sense. So in a lot of ways, I think it's kind of like learning a new language, but once you kind of get used to it and once you start actually using it, then it starts to make more sense. So the plan today is to continue on with our discussion of interest. So I think we just kind of introduced the concept last week, and today, we're going to dive more into that. But before I get started with that, are there just any questions about the class, about last week's lecture, or just anything that I can answer before we get started today?
I think we're good.
Okay. I do have one more announcement. So I did post our first homework assignment. So I think everyone sent me an email, so that's good. I haven't had a chance to enter it to the gradebook just because I've kind of had a lot of other stuff going on. But our first real homework assignment is up on. Naturally I want to say Titanium just because that was the system for before, but it's on Canvas. So it's basically going to be, it looks like a lot of problems, but it's basically covering this. It's basically covering the stuff we did last Thursday and what we're going to cover today, and anything that spills over into Thursday too. So it's kind of a lot of problems, but the problems themselves are fairly short. So hopefully it doesn't take you guys too long. So that'll be due a week from today. So that'll be due next Tuesday. Okay, so let's go ahead and get started today. So where we left off last week was this idea that money has a time value, right? And so the whole idea with that is, if you're given a choice between having money now versus having money later, having the money now is always going to be more valuable. Right? Okay. So the same amount of money that, if you're considering the same amount of money now versus the same amount of money in the future, that same amount of money is more valuable today. And the whole idea with that is that, if you have the money now, then you can actually do stuff with it. You can buy, whatever you want, or you can invest it into and grow, and then have that money grow. Okay. And so the assumption usually is that whenever you're asked to wait for money, or you're considering a future amount of money, that in order for that to be equivalent to money now, then that money should grow over time, right? And then the rate at which that money would grow over time is known as the interest rate. So I think at the end of last week, we did a simple example where, a friend asked you for $5,000 to help him start a business. And then after 4 years, he pays you back that $5,000 plus the interest, right? So we agreed to an 8% interest rate for 5 years, right? So this is an example. Okay. And so what a lot of people noticed last week was that, this problem that we did was we used a non-compounding interest or a simple interest, okay? And so in order to compute the actual amount of interest that was earned over that 5 years, we just took our original principal or the original money that we invested, which was $5,000. Okay. We multiplied it by the interest rate. So the interest rate in this case is 0.08. Okay. And then we multiplied it by the number of times that, our interest is going to be paid out. And so in this case, we are waiting 5 years and we're going to be paid out on the interest once a year. Okay. And so the amount of interest that we make is $2,000. Okay. And so to add it all up, we have 5,000, which is our original principal, which is going to be paid back, plus the 2,000 we made in interest. And so the amount of money that we're going to get in 5 years is going to be $7,000. Okay. Okay. And again, this example that we did here was an example of simple interest where, you compute your interest payments just based off your original principal. And so the formula that we use for this, which we use kind of right here, is that the amount of simple interest that you earn is P, where P right here is your original principal, or the original amount of money that you put into the investment. Okay. I right here is your interest rate expressed as a decimal. So if you have an 8% interest rate, you need to express that as 0.08. Okay. And N right here is your number of periods. Okay. Right. So remember, simple interest, we're just computing the interest payments based off the original principal or the original amount of money that you put in. Okay. So this is, the reason it's called simple interest is because this is a simple formula. You just take, all the numbers in the problem, you just multiply them together. So, it's a fairly simple thing. But in reality, this is actually not what's used all that much. So, you might use this formula if you're just lending money to your friend, for dinner or something, and you want to collect on it, later. This kind of shortchanges you a little bit, because in reality, what banks and what a lot of lending companies do is they use what's called compounding interest. So with compounding interest, what happens is that the interest payments go up because every time you collect on interest, that interest gets added back into the principal. And we'll see how we do calculations for that in a second. Okay? But before we jump into compound interest, are there any questions on simple interest?
No.
Okay, so let's go ahead and move on. Okay, so in reality, what's often used is what's called compound interest. Okay. So we have another definition. I know it's a lot of definitions, but you just got to bear with me for the for the present time. And so the idea with compound interest is that the interest from the previous period, whatever you collected, that gets added into your principal. And what this results in is higher interest payments as time goes on. And so I think the best way to illustrate this is with the example. So let's redo the same example that we did for simple interest, and let's see how that's going to change if we used a compound interest formula. Okay, so let's do an example. So it's going to be the same example as before, but so all the numbers are going to be the same. So let's say that we have an original principal, or original investment is $5,000. Okay. So you're giving $5,000 to your friend to help him start his business. Right? Okay. So we have an interest rate of 8% per year. And then the length of the term, or the number of periods, that's going to be 5 years. Okay. And so same thing, we want to calculate how much money our friend is going to give us at the end of 5 years. But instead of a simple interest formula, we're going to use compound interest. Okay, so I think the best way to kind of illustrate this is with a table. So let's go ahead and do that. So the first column for a table is going to be year. Right? And so let's make a row for every year that we're going to do. So we're going to have year one, year 2, year 3, year 4, and year 5. Okay. And so let's make another column for the principal. So that's what we're going to use to compute the amount of interest. Okay. And so our original principal on year 1 is going to be what I have right there. So we're going to start out with $5,000 principal. Okay, so the next column we have is going to be for the interest. And so we have an 8% interest rate here. So in order to compute the amount of interest that we have, we're going to take what's in the principal column and then multiply it by the interest rate. Okay. And so for this first year, what we have is 5,000. That's our original principal. And then we're going to multiply that by our interest rate, which is 8%. So if we do 5,000 multiplied by 0.08, that'll give us 400. Okay. So in that first year, we're going to make $400 in interest. Okay. And then because this is a compound interest problem, at the end of each year, what we need to compute is the new principal. Okay. And so if we go back to our definition of compound interest, we can say that, or we see that, in order to compute the new principal, what we need to do is we need to take the old principal from that year and then add the interest to it. And that will become our new principal. Okay. So for this first year, we're going to add together 5,000, which is our original principal. Okay. And then to that, we're going to add our interest, which is 400. And so our new principal here is going to be 5,400. Okay. And then we're going to take that 5,400, and then that becomes the principal for the second year. Right. Are there any questions about how I got all the numbers in that first row? Okay. Okay, so now let's do the second year. So the second year, we need to compute our interest. So we're going to do the same thing. We're going to multiply by 0.08. Okay. But instead of multiplying 5,000 by 0.08, we're going to take our new principal and then multiply by that. So we're going to do 5,400 multiplied by 0.08. It's very difficult to write small on a pad. and then that's going to give us $432. Okay. So if we compare the interest payments from the first year to the second year, the fact that we're doing compound interest now, you can see that our interest payments are going up. So our interest payments went up by $32 in the second year. So that's pretty good. So that's an 8% increase right there. Right. So then now for the new principal, we're going to take our old principal, which is 5,400, and then to that we're going to add our interest. So if we add those two guys together, we get 5,832. Okay. And then that becomes the new principal for the next year. Okay, and so we can continue on with this. So, the interest payments is just going to be for the third year is going to be 0.08 multiplied by 5,832. So I'm going to go ahead and fill in the rest of the table with all the numbers. And then at the end of 5 years, what we get is an amount of 7,347. Okay. So if we use a compound interest formula for this loan that we're going to give our friend, then our friend is going to be paying us $7,347 at the end of 5 years. Okay. So if you compare that to the amount that we got for simple interest, for simple interest, all we're getting paid is 7,000. So just by using the compound interest formula, keeping all the other numbers the same, we're making an additional $347, on this loan. Okay, and so you can see why banks and lenders like to use compound interest, because it usually ends up, they earn more money for it. Right? Okay, are there any questions on this example?
I have a question.
Sure. What's up?
My question is this assuming that the person you lend the loan to doesn't make any payments within those 5 years until the end?
That's correct. Yeah. So right now we're assuming that we're giving $5,000 to our friend, and he's going to pay us back in just one lump sum at the end of 5 years. Later on, we'll see how to handle situations on if he wants to pay us like every month or once a year or something like that, and that's what's called a uniform series. So that's typically how people pay back loans, is that they pay it back kind of incrementally over time, and we'll see how we can do calculations on that too.
Cool.
Okay. Any more questions on this example? Okay. So that's compound interest. So, compound interest, because it's a lot more common in reality, from this point forward, we're going to assume that any interest rate that I give you, or any interest problem, is going to be a compound interest problem. So, simple interest is kind of nice just to introduce the idea of interest, but for all practical calculations, everyone uses compound interest. Okay? And just in a little bit, I'll show you kind of a simple formula on which you can use to compute compound interest in this way. Okay. But before we get there, we have to introduce a new concept. So it's a new definition. I know it's a lot, but this one's really important, and that's the concept of equivalence. Okay. Okay. And so we know that money has a time value. So as time goes on, the money that you have that's not growing, it becomes less and less valuable, right? But there's this idea of equivalence where if we compare certain amounts of money at two different time points, so like say we compare an amount of money today versus an amount of money 5 years from now, there's a certain amount of money that you can have that's 5 years from now that's going to be equivalent to the amount of money that you have now. Okay, and so just to kind of give you an example of that, let's go back to our previous example, right? some reason my iPad thinks my wrist is a stylus, but it's not. Okay. Okay. So if I could sum up just the previous example in just a couple lines. So, the $5,000 that you had. Okay. This is $5,000 that you have today. Okay. And then at the end of 5 years, what your friend is going to be paying you is $7,347. Okay. So your $5,000 today will be worth $7,347 in the future. Okay. Through your friend and and loaning your friend that money. And so when we have a certain amount of money in two separate time points, and it grows at a certain interest rate, what we say is that these two guys are equivalent. Which is kind of a weird thing to say, because it's weird to say that $5,000 is the same as $7,347. $7,347. So it's weird to say that $5,000 is equal to that, right? But the difference in between these is that this $5,000 is $5,000 that you have today, right? This 7,347, this isn't the amount that you would have in 5 years. So that all that time has passed, right? And we know that money, the value of money will change with time, right? So if you're going to wait 5 years, to collect or to use this money, you expect that money to grow. Okay? So what we say is that within the 5 years, your money is going to grow to 7,347, and then these two amounts of money are equivalent because they have different amounts, but they're taken at different time points too. Okay. And so in order to compute an equivalent amount of money, you're going to need a few things, right? Okay. Right. And so let's go back to the amount of information that was given to us in that previous example, right? So the first thing that was given to us was a certain amount of money at a certain time. Okay. And so the last part of this is key. So you need to know, it's not enough to know that you have $5,000. You need to know when you're going to have that $5,000, right? Is that $5,000 today? Is that $5,000 a year from now? Is that $5,000 2 years from now? The time is important because as time goes on or as time changes, the value of that money is going to change, right? Right. So the next thing that you need is the interest rate. So you need to know the rate at which your money is either going to go up or go down in value. So the interest rate is what captures that. Okay. And so we were given that in the last problem. Remember that was the 8%.
Professor,
Yep.
how we determine our interest rate, like on what they calculate? They make it like 8%, 10%, 15%, depends on what they make it.
Yeah. So for the purpose of this class, I'm always going to give you the interest rate. I'm either going to give you the interest rate, or that's something that you're going to solve for in the problem. But in reality, if you're going to be borrowing money to, start a business or to buy a certain piece of equipment, the interest rate is set by the lender, the person that's lending you the money. So if you go to a bank or something and you say, you want to borrow $10,000, they're going to say, okay, we can lend you $10,000 and we'll lend it to you at a 2.75 interest rate, something like that. So that's basically set by the person that's lending the money out. And it's not like they set that arbitrarily too. So that that number depends on the economy, depends on what the federal government specifies too. So there's a lot of factors that go into it, but most of the time, it's going to be given to you, either by me, for this class, or by banks, which is where you're most of the time you're going to be lending the money from.
Okay.
Okay. So then if you have these three pieces of information, then you can basically, the way I like to think of it is like, think of it as like a conversion, right? So if you have $5,000 a day and you have, a certain interest rate and you want to see, what it's going to be like, 3, 4, 5 years in the future, then you can convert that $5,000 into a different amount of money that's going to be worth the same in the future. So kind of as we go throughout, and we're going to be covering, how do we convert between different types of money. Think of these as like conversions, because that's, to me, I think that's kind of the easiest way to think about. Okay, are there any questions on this?
Nope.
Okay, let's go on then. Okay, so now let's start putting some formulas to this. So, the way that we solved that compound interest problem before is we used the table, which was nice just to kind of illustrate what was going on. But that's kind of a little bit, it's a little bit annoying to kind of have to write out something like that all the time. And because most of the time you're just interested in is, if you have $5,000 a day, how much is it going to be worth in 5 years, right? And so let's do, I'll give you guys a simple formula for that. The formula is going to be F is equal to P times 1 plus I raised to the n power. Okay. And so now let's define what each of these symbols mean. So let's start with P, because usually P is your starting point. So P here stands for a present sum of money. And so the key word there is present. So that's money that you have today, right? So if you're talking about a loan, this is the amount of money that you have, right now that you want to invest in something, right? And so, present is always going to mean, money that you have right now. Okay. Let's go with this guy next. So this guy is just the number 1, right? So nothing special about that guy. So I in this case is the interest rate, and again, this interest rate is expressed as a decimal. Okay. Make sure that your interest rate is a decimal, right? So you don't want to add the number 8 here. Otherwise, you're going to think that your $10 a day is going to be worth like $1 million in 5 years, which is not the case, right? And so that n is there as the number of periods, right? So if you do 5 years, that n is going to be 5. If you do 7 years, it's going to be 7. So and so you want to be a little bit careful with n, because sometimes the example that we just did, the interest compounds yearly. So the n right there refers to the number of years. But you might also come across cases where your interest is going to compound monthly, so that n might be the number of months. So kind of just pay attention to the wording of the problem, and in real life, check the wording of the actual loan agreement too, just so you kind of know what you're getting yourself into. And so this F right here is the equivalent future sum. Okay. And so the key here is future. Okay. And so if you plug in everything on the right-hand side of the equation, so you plug in a present sum of money, you plug in the interest rate, and you plug in the number of periods, what F is going to represent is an equivalent amount of money, with those statistics that far into the future. And so let's apply the formula to the example, just so you can kind of see how it works. So we have F is equal to P. So remember, P is our present sum of money. So the amount of money that we have now is $5,000. Right. We're going to multiply that by 1. So 1 is just 1. Plus our interest rate, which is 0.08. Okay. And then, we're going to do this for 5 years. Okay. And so you can punch all those numbers into the calculator, and what you get is 7,347. Same amount that we did with the table, but a lot faster, just because we have a formula for it. Okay. And so what this formula is you can think of this as like the single payment compound interest formula. Okay. And so if you want to find an equivalent lump sum of money for something that you have right now, and you know your interest rate and you know the number of periods, then you compute an equivalent amount of money in the future that's worth the same amount as you have right now. Okay. Any questions on this before we move on? Okay. Okay. So that's the F is equal to P formula, but it can also be useful sometimes to kind of manipulate this formula, right? So if we move the interest part over into the denominator, we can have P is equal to F all over 1 plus I raised to the n power. And so the names of all these symbols are the same, but I just rearranged it so that now we're solving for P instead of F. And so this can be useful where, like, if you have a future sum of money in mind, so like say you want to save up a certain amount of money in the future, say you want to stash some money away in the bank, you can find out how much money that you need to invest right now. Okay, so let's do an example to kind of illustrate this. Okay. So in this example, let's say that in 5 years, what you want to have is you want to have $1,000 in your bank. Okay. And so let's say that this bank account has an interest rate of 2%. Okay. And so if you want to have your $1,000 in your bank account in 5 years, what you want to know is that how much money do you need to put away right
Is it a 2% or 27?
now? It's a 2%. Okay, so in this problem, we have a future amount of money. So we have a F is equal to $1,000. Okay. Right. So our interest rate is 2%, and then our N is equal to 5. Okay. And so the only thing that we don't know in this problem is the P. So we don't know what the present amount of money that we need to put away into the bank right now. Okay. And so let's just use the formula that we have at the top of this page and just kind of plug everything in, right? So our F is 1,000. Okay. Our interest rate is 2%, so let's do 0.02. Okay. And then we do this for 5 years. And then what we get is $905.73. And so if you want to have $1,000 in 5 years, and you have a bank account with a 2% interest rate, you have to put away $905.73 in order for you to get that $1,000 exactly. Okay. All right. Are there any questions on this example?
Also, you may ask about like in how many years you could get like a certain amount of money, so we could like manipulate the equation and do like the natural log, get the n by itself and these stuff.
Oh, absolutely, yeah. So we just did examples here where we're solving for P or F, but you can solve for N or you can solve for I too. So like another way to phrase this question is say that, say you have $900 today, and you want to have $1,000 eventually. The interest rate is 2%. So you can say, how long will it take for that $900 to grow into $1,000? So in that situation, you would solve for the N in that equation. Yeah. Right. Okay, so that's an introduction to compound interest problems. So we have P and F right now. So I want you guys to kind of remember the definitions of P and F. Okay. So those are going to be members of our I call them the cash flow family. So those are kind of the two kind of basic cash flows. These are kind of the single payment cash flows. And then what we'll learn maybe today, but it might spill over into Thursday, is how we can get different kinds of cash flows, like maybe like a uniform series where you make payments constantly. And then there's going to be one more after that called the arithmetic grid. Okay? So P and F, those are kind of our the first two members of our family, and then we'll see how the other members kind of fit in after that too. Okay, but first, I want to take a bit of time to explain the difference between interest rates. So right now we've just been using interest rates just by itself. But in reality, you're going to come across different kinds of interest rates. So I just want to make sure that you guys kind of know the differences between them and how to convert between them. Because especially if you watch any daytime television, you'll see a lot of commercials for like auto loans and stuff like that, and they'll throw terms like APR, APY. So it's good just to kind of know what these terms are. Okay? Unfortunately, this means more definitions, but that's just kind of the nature of the first couple of weeks of a class that's basically an all new subject, right? So we're going to talk about nominal versus effective interest rates. Okay. And so, whenever you see advertisements for like loans, you might see billboards on the freeway. You need to know, and then they tell you an interest rate. It's good to know whether they're reporting it in nominal or effective, because there are some slight differences between them. Okay? So let's go ahead and define this. First, let's start with nominal interest rate. Okay. And so the common term that you'll see for this in advertisements is APR. And so what the nominal interest rate represents is the annual interest rate without taking any compounding into account. And so this is important because a lot of times, if you buy a car from like a dealership or something, they might say that, we have like a 2% APR. And so what that means is that the 2% is going to be applied every month. But what you often want to know is, what is my interest rate going to be for the entire year? So just an example of this. And so let's say that, you have a savings account with the bank. And what the bank says is that this savings account is going to pay out 2% every 4 months. Okay. And so the nominal interest rate, which is, the interest rate that you're going to earn for the year, is simply just going to be 2% multiplied by the number of periods. Okay. So in this case, since the bank pays out 2% every 4 months, in a year, your bank's going to pay out 3 different times, right? Because a year has 12 months. And so if it pays out every 4 months, then it's going to pay out 3 times a year. Okay. And so the APR for this bank, for this bank account is going to be 6%. Okay. And so the other definition I want to go over is effective interest. So this often has the name APY. And so the difference between APR and APY is that effective interest rate will take compounding into account. Okay. And so if we take our bank account example again, so the bank paying out 2% every 4 months, right? So in reality, what's happening is that the bank is actually going to be computing compound interest. So every 4 months is going to pay out 2%, but the 2% that it pays out is going to be added to your bank account. So that 2% is going to be added to your principal. Okay. And so the way that we're going to compute the APY, or the effective interest rate, is using the same formula that we did for the compound interest from before. Okay. And so let's take the interest rate. So the interest rate here is 2%. Okay. Okay. And we're going to add 1 to it, and then we're going to raise it to the number of periods that we have. So in this case, we have 3 periods. And so to get the effective interest rate, we're going to add 1 plus 0.02, and then raise that to 3 pounds. Okay? And then what we get is 1.061. And so if we multiply this by 100, then we get a effective interest rate of 6.1%. And that's going to be our APY. All right. And so since most applications are going to use compound interest, the APY, or the effective interest rate, is going to be more useful, especially with all the formulas that we went over earlier today, and in the future, all of those are going to assume that the interest rate is going to be the effective interest rate. Okay?
Professor?
Yeah.
1.061 times 100, or is it just 0.061 times 100?
Oh, it's 1.061 times 100 minus 100, so then you get 6.1 from that.
Oh,
so, yeah.
All right. Thank you.
Yeah, so I skipped those steps because I kind of just see that as kind of the percentage over 100. So yeah, that 6.1 is kind of the percentage that it grew. So you can the way you can see that is that we start with 1 here, and then through the growth we end up with 1.061. So our original 1 has grown by 6.1%. That's kind of another way that you can do that as well. Okay. Right, so the effective interest rate, that's going to be more useful, and then that's the one that you're actually going to plug into your formulas that we did before. So just be careful. So if you're reading a problem, or you're doing your own calculations of personal finance, and they give you something in APR, before you plug that into the formulas that we have, make sure that you actually compute like the effective interest rate, or the APY, because that's what's going to be that's what's going to give you the more accurate answer. Okay. All right. Are there any questions on this? Okay. And so so you can convert between the two. So there's a formula which you can do that. Okay. And so the formula to convert is given by this. We have IE. So IE right here is our effective interest rate. So IE is going to be equal to 1 plus R over N. Okay. And where R right here, this is your nominal interest rate. Okay. And then we're going to raise that to N. So both those N's are the same. So those N's are going to be the number of periods. Okay. And then from that, you're going to subtract 1. Okay. And so that's the formula where if you have a nominal interest rate and you want to compute the effective interest rate, this is how you would do it. Okay. Another thing that is useful to know is where, if you go to a bank and they say that, they offer something with continuous compounding. So what that means is basically that, your money is compounding all the time, basically. It's not waiting for every 3 months or every month or every year. So it's always compounding, so it's always growing. Okay? And so the formula, in order to compute the effective interest rate from a continuous compounding situation, is given by the following. So we have IE is equal to E raised to the R minus 1. Where R right here, this is the continuous nominal interest rate. So, in this class, we're not going to do too much with continuous compounding, but I wanted to show you guys this formula. So, if you're ever out there, you want to get a loan or something, or you want to invest money in a bank, banks, they often like to throw a lot of these confusing terms at you just to get you to sign and make things sound good. So, if they tell you something is continuously compounding and you want to actually compute the effective interest rate to see how much money, you're actually going to make, this is the way that you would compute that. Okay.
Professor?
Yeah.
I just have a couple of questions. So if you're doing this for more than a year, you'd have to involve time, like in the exponent?
Yes.
Okay. And then the other question is kind of where this formula comes from and how we get base E. does it come from like a limit? Because I tried to think about that a little bit and I couldn't get this formula out of a limit.
Yeah, yeah, yeah. No, you're absolutely.
Infinity.
Yeah, no, you're absolutely right. So it does come from a limit. I don't have the derivation in front of me, so I would have to look it up. But it is something that involves, usually this R is something that's pretty small. And so it kind of the limit of kind of a small number like that, and you kind of, you take kind of an infinite sum, an infinite series, and you kind of take the limit of that, then this is what you end up getting. Right?
Okay.
Yeah.
Thanks.
All right, so there's a question from the chat is do we have to memorize these formulas or are they going to be given to you on a quiz? So for all my, well, I mean, this semester is kind of special because it's, it's all virtual. So, I can't stop you guys from using your notes on the exam. So you can do that. But normally, for the exams that I give, I let everyone have a formula sheet where you can put these formulas. Because I personally feel like memorizing formulas is a waste of time because you're never going to be in a professional setting where like someone's gonna like point a gun at your head. It's like, give me the formula for compound interest. That's never gonna happen. You're always gonna be given a problem, and you're gonna have access to your computer and all your notes and all your resources. So, I think there's no point in making you guys memorize the formulas because it's not something that you're gonna be asked to do in reality too. Yeah.
Professor?
Yeah, what's up?
I'm not sure if I understood right, but did you say we have to add effective interest into nominal interest?
So they're just two different interest rates. And so, the idea with nominal interest and effective interest is, usually the year time frame. So, knowing how much money you're going to make in a year, that's usually kind of a good reference point. But a lot of times you're going to come into situations where, you're going to have a bank account or something that pays out every month or every 2 months or something like that. And so to convert that to a year, this is how you would do it for, the nominal interest rate and for the effective interest rate. Yeah.
Okay, thank you.
Yeah. So usually we like to do economically, we like to do things on like a year horizon. So this is how you would, convert things to like an annual interest rate. So that was kind of the point of this whole thing. Yeah.
Sounds good. Thank you.
Yep. All right. Any more questions on nominal versus effective interest rate before we move on? Okay. So that was kind of a, it was in the grand scheme of things, it was kind of a detour. So now let's kind of get back to the different cash flows.
Professor, I have a quick question.
Sure.
So on the exam or on the quiz, are you going to tell us which like formula do you need us to use, or we need to think about it and determine which one we have to use?
Yeah, so part of these economic problems is that, you have to kind of determine what formula you need to use. So, I mean, there will be hints in the problem where, so far, at least with regards to cash flow problems, we know, we know the present sum and we know a future sum, right? And so usually the verbiage in the problem will kind of tip you off as to, which one to use. And so what we're going to learn next is the uniform series. And so, the way that you are tipped off for the uniform series is that, this is a payment or this is a benefit that you get that occurs on a regular basis or a recurring basis. So that's kind of the hint to do that. So I'm never going to tell you, use the F and P formula or use the A and P formula, but that's something that you have to figure out just from the context of the problem. Yeah. Okay. So the next thing we're going to learn is uniform series. A uniform series with compound, that should say interest. Okay. And so there are already some questions about this. And so the idea with the uniform series is that it represents a series of payments, a series of uniform payments. That's why it's called a uniform series. And so, if this is kind of the traditional way that people pay back a loan. So, say that you want to borrow like $1,000 from the bank, you borrow that from the bank, and then instead of paying all that back in one lump sum at the end, the way that people typically pay back on loan is that they pay it back, every month you pay back, maybe like $110 or something like that. Okay? And so the symbol that we use for uniform series payments is A, right? So we know F and we know P. So P, remember, is one lump sum of money that we have in the present day. F is one lump sum of money that occurs at the end. Okay? And so A, what this represents is a recurring payment, okay? Or more specifically, an end of year cost or benefit. Okay. And so I'm going to give it the symbol A, which is weird because the letter A does not occur in uniform series at all. But the reason it's called A is because oftentimes when we think of uniform series, we think of payments that happen at the end of every year. So a yearly thing is known as an annual thing. So this A basically stands for annual. So that's where the A comes from. So this is probably the weirdest one because we call it a uniform series, but there's no A in there, but we use A. Okay? And so schematically it might look something like this, right? So if I draw the cash flow diagram for it, okay? And so let's say that we can use A to represent your paycheck that you get every month or something, right? And so let's say that at the end of every month or at the end of every year, so let's just say that you get paid once a year for this job, you make the same amount of money A, okay? And so that's what this represents. So the A represents the amount that you get paid or the amount that you pay out at the end of every period, okay? And so what this means is that if you, when you actually compute A from like, a single present sum or a single future sum, this A is going to be a lot less, right? And that's okay because remember, A is paid out to you at the end of every period. So, A is the amount that you pay at each period where, if you add them all up together, then it's going to add up to either a present sum or a future sum. Okay. And so what we want from this section is we want to have formulas that will allow us to convert between A and F and A and P. Okay. And so this is really useful to say, like, say that your friend wants to borrow the $5,000 from you, but he doesn't want to wait until the end to pay it back. So if he's going to pay you every year for that $5,000 with the 8% interest, then, he wants to compute, how much he has to pay. And then these formulas are going to allow us to do that. Okay. All right. Are there any questions on this? On just the concept of a uniform series?
Can you explain the last line?
Yeah, so the last line there is, we've gone over two formulas so far where, we can solve for F given P. We're assuming that we know the interest rate and we know the number of periods. And so if we know the interest rate and the number of periods, we can compute F from P, or we can compute P from F, right? So those are the two formulas that we saw before we launch into our discussion of nominal versus effective interest rates. And so we want to have similar formulas for A. And so say that, we have a present sum of money, and we want to, extend this over like a 5-year period with an 8% interest, what is that uniform series payment going to look like? And that's basically what we want to do. So we want to have formulas to compute this stuff. Yeah. Right. Okay. So in the notes, I go through a derivation for this. So definitely take a look if you're interested in that. But just by the nature of virtual teaching, things tend to go a little bit slower than I wish. So I'm just going to give you the formula, just because the derivation, it's nice to know, and it's kind of a fun math exercise. But within the grand scheme of economics, it's not the most important thing. So I'm going to give you the formula for F and A first. Okay. Okay. So it's a little bit more complicated just because a uniform series is just a little bit more of a complex beast than just single sums of money. Okay. Okay. And so let's define everything here. So F, remember, is a single future sum of money. A is the uniform series amount. Okay. So this is like the recurring payment or the recurring benefit that you would have. Okay. And then on the right-hand side, we also have I, which is still our interest rate expressed as a decimal. And we also have N, which is a number of periods. Okay. And so if you know the uniform series amount, you can compute what that's going to be equivalent to in the future. Or if you have say you want to have a future sum of money, you can use this formula and you can invert it and then use that to compute A. Okay. And so let's do an example just to kind of show this formula in action. Okay. And so let's say that we have a couple friends of yours just got married and they're interested in buying a house. Okay. And so they want to start to save money for a down payment. Okay. And so to do this, they want to deposit their money into the bank into an account with an 8% interest rate. Okay. 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 And so into this account, they're going to make a deposit of $5,000. That's their initial deposit. Okay. And then each year after that, they're going to make a deposit of $7,500. Okay. All right. And so what they want to know is that after 2 years of this, how much money is going to be in their bank account. Let's see. And just to kind of bring in some information from before, let's say that this 8% interest rate right here, this is the nominal interest rate. And so the first thing that we're going to do is we're going to take this nominal interest rate and we're going to convert it to the effective interest rate, just so that we can actually use our formulas. Okay.
Can you repeat this part again? The difference between the nominal interest rate and the interest rate?
Yeah. So the this nominal interest rate, basically this is the interest rate without taking compounding into account. Okay. Oh, and the other piece of information you need to know is that this bank account will be compounded monthly. Okay. So it's be compounded every month, right? And so this 8% is the is the annual interest rate without taking compounding into account. And so the first thing that we need to do is we need to compute the effective interest rate, which does take compounding into account. Yeah. And so we're going to use the formula that we went over a couple slides ago on how to compute the effective interest rate from the nominal one. Okay. And then from there, we're going to use the other formulas that we have in order to compute what the problem is asking.
Professor?
Yeah.
So how would we know when we're giving the nominal or the effective rate?
It's I'll tell you. So I just forgot to put it in the main text for the problem. But the main text actually does say that this is a nominal interest rate. So I would tell you if it's nominal or effective.
Okay, so if we're giving the nominal and it's compounding, just use the formulas to get the effective rate.
Yeah. So we'll go over that in a second once we start solving the problem.
Thank you.
Mm-hmm. Okay, so let's do that first. So let's compute the effective interest rate from the nominal. So we're going to use the formula IE is equal to 1 plus R over N, all raised to the N power minus 1. Okay. And so let's plug in the numbers from the problem, right? So we have 1 plus R. So R is our nominal interest rate. So in that case, it's going to be 0.08. Okay. Next, we have to plug in N. And so since this nominal interest rate is compounded monthly, we need to compute how many months are there in a year, right? So there's going to be 12 months in a year. So let's plug in 12 for this N. Okay. And then raised to the 12th power. And then what we get from this is 0.083. And so this gives us an approximately 8.3% APY. Okay. And so from this point forward, we're going to use 8.3 for the interest rate for all the other formulas. Okay. And so now that we have the actual interest rate, let's go about actually solving the problem. Okay. And so there's kind of a lot going on here. So let's kind of break it down. And so the first thing that we need is we know that we made an initial deposit of $5,000. Okay. And so in order to make an initial deposit, we need to have this money on hand today. Okay. And so since this is a money that we have in the present day right now, then this is our P. Okay, so our P in this case is going to be 5,000. Okay. Okay. And so after that, the problem says is that the couple is going to make a deposit of $7,500 every year. Okay. And so this is a recurring payment into the account. Okay. And so since this is a recurring payment and it's in the same amount every single year, this is going to be our A, because this is going to be like our annual payment into the account. Okay. And so, and what the couple wants to know is how much money are they going to have after 2 years? Okay. And so 2 years is some point in the future, right? So we want to know how much money are we going to have in the future. And so that's going to be our F. And so the way that we're going to solve this problem is we're going to take our interest rate, which is 8.3, and then we're going to convert our two cash flows. First, our P of 5,000, and we're going to convert that to F. And then we're going to take our A of 7,500, and then we're going to convert that to F2. Okay. So we're going to apply two different formulas here. So let's start with P. Okay. And so the formula for this is we have F is equal to P times 1 plus I all to the n power. Okay. Right. And so let's go ahead and plug in the numbers. So we have 5,000 times 1 plus 0.083. Okay. And so our n in this case is 2 because we have 2 years. Okay. So let's go ahead and plug in 2. My iPad will cooperate. Okay. And so that initial $5,000, which we leave in the bank account for 2 years, after 2 years, the couple is going to have $5,864.45. Okay. Okay. Any questions on that? Right. So the question is that if it says compounded more than once, it should be an effective rate. That's right. So anytime it's compounded monthly or something, then that's a good hint that you need to compute the effective interest rate. Okay, so we're almost out of time. So I want to finish up this problem. Okay. So that's the first part. So the second part is we have that $7,500 that we're making a deposit every year, and we want to see how much that is going to be worth in 2 years. Okay. And so we're going to use our F is equal to A formula. Okay. So this is the one that we just went over. Okay. Let's go ahead and plug the numbers in. So our A is 7,500. So that's the amount of money that we're putting in every year. Okay. Okay. And we plug in our interest rate and the number of periods. And then what we get is 15,622 and 50 cents. Okay. Right. And so now that we have the future sum with respect to to our initial deposit and the future sum with respect to the deposit we're making every year, we can just sum them up. Okay. Okay. So the total F is going to be 5,864.45 plus this 15622.50. Okay. And it's going to be 21486.95. Okay. Right. So in 2 years, if the couple keeps depositing $7,500 each year, then their bank account is going to have $21,486.95. Okay.
Would you mind if you summarize it very quick?
Yeah, sure. Right. So the problem asks, if we make an initial deposit of $5,000 and we make a deposit every year for $7,500, how much money is going to be in the bank? Okay. And so we broke this up into 2 parts. So the first thing that we computed was the equivalent future sum of our initial deposit of $5,000, which is what we did right here. So that was our F and P formula. And then after that, we computed the equivalent future sum of the yearly $7,500. So since this $7,500 takes place every year, then we consider it a uniform series, or an A. Okay. And then we plugged into the formula and we got that. And then we just added them up together in the end, which was 21,486. Yep.
Thank you. Yeah.
All right. Any final questions on this example? We're a little bit over time.
Yeah, I have a quick question.
Sure.
So 7,500 was only put in the account after the first year. So
Yes.
why do we?
Oh, sorry, you got cut off a bit.
Oh yeah, so I was saying, why do we make an exponent of 2 years even though the 7,500 is only put in for 1 year?
So it's put in at the end of every year. So if we draw the cash flow diagram, it will look something like this. So there was actually 2 deposits here. Okay. I will do that. And
I
so
think I just
initially,
misread the question then.
yeah. So initially we have 5,000, and then at the end of every year we have 7,500 like that. Yeah. So there are 2 payments. That's why it's a little bit more than 15,000. Yep. All right. Any final questions on this? Okay. So I apologize for going over time a little bit. So thank you everyone for tuning in today. So the recording for this will be up, later today. And then on Thursday, we're going to finish up these lecture notes and maybe start the next one on present worth. Okay. All right. So thank you everybody for tuning in. Have a great day, and I'll see you guys on Thursday.
When's our homework due?
Our homework is due a week from today, so it'll be due next Tuesday before class.
Thank you.
All right, and I'll stick around for a few more minutes if you guys have any questions too.
Yeah, Professor, I have a quick question.
Sure. What's up?
Can you just explain to me real quick why we use the effective interest rate right away? Like, what was the reason again?
Right. So remember, the effective interest rate takes compounding into account. So,
Okay.
basically every problem that we're going to do, we're going to assume that, we're going to have compound interest.
Okay.
And so, whenever you have compound interest, you need to use an interest rate that takes that compounding into account. So that's going to be the effective interest rate. Yeah.
All right, then. Thank you.
Yep. Mm-hmm.
If it doesn't ask for a compounding interest, you would use a nominal interest rate?
So if it doesn't say anything in the problem, you can assume it's an effective interest rate. But you actually can't, with the formulas that we're going to be learning in the class, you can't actually use the nominal interest rate for that because you're going to get the incorrect results. So if the problem explicitly says that this is a nominal interest rate, you need to convert it to an effective one before you can actually use the other formulas.
Okay, thank you.
Mm-hmm.